Welcome to EK Lectures. Here are few more questions that we have posted on our Telegram channel. Let us discuss one by one. In a BJT, collector base and the base emitter junctions are forward biased. Then the transistor is in which of the following state? Now here you have a forward characteristic curve for transistor where this is IB. All these values are for IB and the lowest value is IB equal to 0. Beyond or lower to this point you have no current IC, no IC is there, which means your transistor is not working. Okay, at this point the transistor is not working and this region is called cutoff region. Cutoff, which means transistor is off. Now as and when you increase your IB value increases, you are reaching into a point where it is called active region. And here the amplification of the current IB occurs, which is IC is equal to beta times IB, where beta is the current amplification factor. Now again further, if you increase, you reach into a region called saturation, where you have maximum value of IB and maximum value of IC, beyond which you cannot increase the value of IC. Now coming to the question, both collector base and base emitter regions are forward. This is such condition. Now look at this area. Since it is both the junctions are forward, literally you don't have any potential barrier here. The potential barrier is negligibly 0. Now when there is no potential between these two, it acts as a pure conductor. Pure conductor means whatever IC is flowing or emitted by the emitter region, it automatically gets into IC. So IE equal to IC equal to maximum, and you have maximum IB also. IB is equal to maximum. And in these two regions, saturation and cutoff region, your value for this formula IC equal to beta times IB is not valid. Only in the active region it is valid. Now look at this table. Collector base and emitter base regions are given. If both are forward, you have saturation where IB equal to maximum and IE equal to IC. And when both are reverse bias, you have cutoff region where all the values of current are 0. And these two conditions or these two states together, it's used for switching purpose. Using the transistor as a switching purpose, you use these two conditions together. On and off state. When it is in off state, your transistor is in cutoff region, and when it is in on, it is in saturation region. Okay. Now, and when the bias and the emitter base junction is forward bias, you have an active region where your value of IC is equal to beta times IB. So your answer to the question is saturation region. Which among the following has the maximum packing efficiency? Now what do you mean by packing efficiency? Volume of the atom occupied by volume of the unit cell. Now coming to the simple cubic, you have edge length is equal to 2 times R. Now what is edge length per atom? Edge length per atom, number of atom is 1, so edge length per atom remains 2R. Now why we are worried about edge length per atom? Because this would tell you volume required to occupy, volume required by unit cell to occupy one atom. So higher the edge length per atom, smaller will be the efficiency, packing efficiency. Packing efficiency will be smaller, inversely proportional. Now coming to the body centered, you have edge length is equal to 4R by root 3. This is A, this is A, this would be root 2 times A, and this length would be root 3 times A. Pythagoras theorem. Now this is R, this is 2 times R, this is R. So 4R by root 3 will be equal to A. So number of atoms here is equal to 2. So dividing by 2, you will get 1.15 R. Here the packing efficiency is 68%. Now, for hexagonal close packing, you have A and B equal to 2R and C is equal to under root 8 by 3 times A. Now this is your A, this is B, and this is C. Number of atoms is equal to 6 and the packing efficiency is around 74%. Now the base centered. Base centered is similar to that of simple cubic. Only thing is that we are placing one more atom in between. This placement of atom shift the corner atoms again towards the end, providing or giving way for more void spaces. When there is more void spaces, your efficiency will reduce and the packing efficiency get reduced by 37%. And the number of atoms here for base centered is 2. Another structure is face centered. Here you have 2 R, R and R. This is nothing but 4R. This is A and A. This is nothing but root 2A. Edge length per atom is 0.707 R and the packing efficiency is 74%. From the question, it is hexagonal close packing. Face of the complex number 1 minus I into I in the polar representation. Now let us see what is 1 minus I into I is equal to I plus 1, which is nothing but 1 plus I. Now in Cartesian form you can write the complex number as z is equal to x plus iy, where x is equal to 1 and y is equal to 1. So x equal to 1 and y equal to 1 means both are positive. That means your complex number is in the first quadrant. Now you need one more parameter, that is theta. Theta is nothing but tan inverse of y by x, which is equal to tan inverse 1. So what your value is pi by 4 and 5 pi by 4. Now in polar representation you can write the complex number z is equal to r e power I theta. Now what is this value of r? R is equal to under root x square plus y square, which is nothing but under root 2. Now theta value you already know, 45, because you know that it is in the first quadrant. So this will be your r, complex number with 45 as the face. So face is 45. An isotropic dielectric offers a refractive index of 1.5 to the propagation of plane monochromatic wave. The dielectric constant. You know that the refractive index is nothing but the ratio of speed of light to that of a medium. Now for any medium, the velocity is given by 1 by under root mu1 times epsilon 1. Now, so you can write refractive index as under root mu1 epsilon 1 divided by mu naught epsilon naught. Now, for a non-magnetic material, mu1 and mu naught are equal to 1. So, your refractive index is nothing but epsilon 1 divided by epsilon naught, which is nothing but root k. So, k is equal to n square. So you are given the refractive index 1.5. So the value of k is equal to 1.5 squared, which is nothing but 2.25. The answer is C. What is the expectation value of Z component of the ground state of hydrogen atom with Bohr radius equal to A? Now you have the wave function of the hydrogen atom in ground state is equal to 1 divided by pi a naught cube under root e power minus r divided by a. Now how do you find out the expectation value? Expectation value of some z is equal to integral psi star z psi dx or d tau, because you have 3-dimensional hydrogen atom is a 3-dimensional problem. So this is the value of expectation value. Now you have to find psi star, and you get the value. But you need not go with all these values, because you know that z is nothing but r cos theta. Expectation value of z is nothing but expectation value of r into expectation value of cos theta. Now expectation value of cos theta is nothing but 0, so your answer is 0. The refractive index of a medium do not depend on. To understand that, we have different glass slabs kept for the experiment. Now temperature. When the temperature increases, the density of this glass slab decreases. Density decreases, as well as viscous property also decreases. So when temperature increases, what happens? The refractive index decreases. This can be one of your subject for project work if you are in BSc. And surrounding. Now you are measuring the refractive index of the glass slab in two surrounding. First you have taken the air as the surrounding, and in the second case you have taken the water. Okay. Now what is the refractive index formula? N2 by N1. Okay, so here N1 refractive index is 1 and N2 refractive index 1.5. So the refractive index of the material is nothing but 1.5. Here the water has a refractive index of 1.3 and the glass slab 1.5. So in effect N2 by N1 is nothing but 1.5 by 1.3. Again the refractive index differs. So the surrounding also affects the refractive index of the medium. Now coming to the color of the light used. Now you have two different colors. One is blue and red. The more bending, the more will be the refractive index. Which one bends more? The blue light bends more than the red light. So blue light, when you use blue light to find the refractive index, you will get higher value of refractive index than when we use with red light. Okay. This is how you see a question in our Telegram channel. This is our Telegram channel name, and under that you will get the question and 4 options. The moment you view the question, you will know that how many person have viewed out of these many subscribers, and you will also know how many person have answered this particular question. Now you know that this answer to the question is 0, and the moment you click here, you will get how many person have answered it correctly. And see, 53% of them have answered correctly, and the remaining 47 has got wrong. Now this gives you an advantage, that it gives an exam experience of doing the problems, and also you can analyze each question, where to focus on your exams. See, out of 85 people who viewed, only 17 of them has answered this, which means only 1/5 is answered, and out of that only 53% of them has made it correctly, which means the rate of this question is very high. So you have to focus on these type of questions more. So this analyzation also can be made through our Telegram channel. So please join our Telegram channel and start doing your problem. The answers to the problem will be discussed here in our YouTube channel. These are the analysis of each question that we have discussed. The most favorite question here is this related to solid state physics with hexagonal closed packing, that around 77% of them has made it correct. And the least favorite question is here with 39%, refractive index of a medium. So this is how you can analyze your answers to all these questions. So this is our Telegram channel, CSIR Net IIT Jam Physics, and this is the link to our Telegram channel, which is also given in the description below. And if you like the video, please like, share with your friends, and also subscribe, and enjoy learning physics with VK lectures.